Okay, in that case, we can move on. And this is where I'm going to be able to answer your question. You can, the idea of generating adversarial examples, adding them to your training data, and then retraining your neural network, you can specify it in the form of a saddle point problem. You have your loss function, you keep perturbing your images, and you're doing it yourself. So nobody else is attacking you, you're just doing it yourself. You perturb your images, and you want your perturbed images to be classified as the original image that you just perturbed. Your perturbations are not going to be too big, and that's how you're going to define them. Maybe you put an L infinity norm, L0 norm, L2 norm here. That's going to define the space of perturbations. And then you have an adversary. What is the adversary going to do? Is going to try to maximize your loss, trying to make you make a mistake, trying to force you make a mistake. So that's what your adversary is doing. But you are going to keep sampling from your training data, and you're trying to basically minimize your loss. Your adversary is trying to maximize your loss. You're trying to minimize your loss. And then the way that you're going to do this is one iteration of delta, which is equivalent to keeping adding adversarial examples to your training data. At the same time, you are trying to classify them correctly and be robust with respect to them. And there's a huge field about robust optimization. And it turns out that some of the methods that we covered, like fast gradient sign method, is just one iteration of this saddle point optimization. So you take a step towards increasing the loss by adjusting delta, or you can take multiple steps. And this one we also saw before, projective gradient ascent, trying to solve this maximization. And to answer your question, how robust are you in the end gonna be? That depends. Does your adversary is a white box attacker? Does it know what type of neural network are you using? What type of architecture are you using? And they can still be effective. They can still be effective at making you mistake. Maybe it's not 100% mistake anymore. And at the same time, some of these methods are more effective than others. For instance, this projected gradient ascent is going to be more effective in making you make more mistakes, despite the fact that you trained your neural network by taking this fact into account that you're going to have adversaries. But this is not 100%. And even these small mistakes, reducing the accuracy is going to be important, even if it is not 100% mistake. Maybe that stop sign that you're mounting on the road is going to make 10% of the cars make a mistake, or even 1% of the cars make a mistake. And that's going to prove to be deadly. Okay? One accident is enough. And even in the face of being black box attack, or the adversary having a copy of your neural network, don't having the type of data that you have, they're going to still be able to attack you. It's not perfect. It's not as good as before, but it is still effective. So this is still a serious problem. I hope this answers your question.
Sort of. So I guess let's say that you go through like these iterations where you generate a set of adversarial examples, you retrain the network, and then you find another set of adversarial examples using the same method. And it's to minimize some LP norm of the perturbation. Mm-hmm. If you were to plot a graph of the LP norm of the perturbation versus these iterations of you retraining the network, how would that look?
I think that's a good idea, but you should take this into account that it's not like you're gonna first train your neural network fully, pick a couple of examples or your entire data set, perturb them, and then retrain. So no, this is not how the process is going to work, because that's going to take you forever.
Right. And
you're going to do it on the fly.
Sure. And I guess I'm assuming this is like a total hypothetical example. Computational cost is not a problem. Obviously it is. But yeah. If this process of adding adversarial examples to your data really was an efficient way of making your network more robust, then I would imagine if you plotted that sequence of LP norm perturbations, that it would be like exponential. So the more perturbations, the more adversarial examples you add to your network, you would have to make your perturbations exponentially larger to create another adversarial example.
Yeah.
But I feel like we can't even guarantee necessarily that one iteration of this will make the next minimum LP norm perturbation larger, because we retrain the network, we restructured the entire network on us when we added this set of adversarial examples. So do we even know that adding adversarial examples will minimize even further the LP norm perturbation the next time we try to do this?
Yes. I'm sure you're trying to look at it in an iterative fashion and then try to look at your LP norm of the maximum perturbation. I haven't seen a plot like that, but maybe this plot is helpful. If the adversary is having a perturbation that is smaller than the perturbation that you used to train your neural network in a robust fashion, then they are not going to be that effective. But as soon as they go beyond that, beyond the perturbation that you tested or you used, they're going to be more and more effective. But there is no perfect answer here how things are going to work theoretically or even empirically, because not only this is costly, these are usually nasty optimization algorithms with a lot of local minima, and even this guy has a lot of local maxima. So yeah, there is no perfect understanding of what is going on here. Okay, and maybe you can actually write a paper about it. Try to keep adding adversarial examples to your training data, perhaps on a simplified data like MNIST, and see what happens. Look at the LP norm of your perturbations and see what is happening. Intuitively, you need to have more and more, bigger and bigger epsilons, bigger and bigger perturbations. And this is an indication of that. You become more robust, but it is still not perfect. You are much robust than before. Previously, if you use PGD, you can bring this number, the accuracy, to 0 as an attacker. Okay? I hope this answers your question to some extent.
Yeah, that was good. Thank you.
Any other ones? There is a good question in the chat. Yes, you keep adding these adversarial examples on the fly to your mini batches, but is there a chance that this process is going to hurt your natural image accuracy? There is a chance, and that depends on the capacity of your neural network. Maybe you're increasing the robustness of your neural network at the same time decreasing its accuracy. This could happen, yeah. But the higher is the capacity of your neural network, deeper, wider, better architecture, then your neural network has the capacity to not only learn your natural images, but also your adversarial examples. Try to be robust. Does that answer your question? Yeah, that's a good observation. Any other ones? And this framework, this saddle point problem, is actually, we can generalize it. The loss that your adversary is using doesn't have to be the loss that you're using to train. Or maybe you can use multiple losses. Maybe you have multiple different adversaries using different losses to attack you. Okay, that's an idea to explore in the future. Any other ones from here? Okay, perfect.